now we can get going. All right, so last class we started talking about double integrals, right? And we used the double integral to find volumes below surfaces down to the xy plane, right? And the region that we were looking at, the domain, I guess you could say, was restricted to a rectangle on the ground, right? And we had almost finished this section up, but there was one last thing at the end that I didn't get to talk about, and that is the volume between two surfaces. So in my Cal 2 class today, what we did is we said, in Cal 2, remember you figure out what the area below a function is, what we mean is the area from the function down to the x-axis. And then the next thing you cover after that, which I covered today, was when you have two functions, right? You have an f and you have a g, you're trying to find the area between them, right? It's kind of still going to use the integral, but you've got to take one function and subtract the other. Well, that's the exact same thing we have here. That's the last little note, is that if you have two surfaces, right? If you have two surfaces, can you all see this? It's kind of, sometimes when you look at these 3D things, it's like you have to kind of like blink your eyes or close your eyes and look again, and then it like kind of comes into focus. This is like a top surface. Okay, it's like a top surface, which I'm calling f of xy. The bottom surface is that reddish one. Okay, that's the boundary of that bottom surface. And so if we want to know the volume of the solid between the two surfaces on top of this rectangle, then all we have to do is take the volume of the top one, subtract the bottom. Do you see it? Do y'all see the two surfaces? And you're looking at the solid between them? Yeah? So the formula, is right here. All it is the double integral over the rectangle of the top surface minus the bottom surface, and then with respect to area. So there's nothing new other than you're just subtracting the two. And that was the last note. I'm ready to move into the next section. I don't have an example for that. We're going to do examples, so I'm ready to move into the next section. So for 12.2, whoa, I have all those errors. So for 12.2, we are now going to find double integrals over general regions. So remember, 12.1, we had on the ground was a rectangle, and then we had a surface above it. Should I draw it again, or do you understand what we did in 12.1? You sure? Okay. So we have this. That's what we've done, right? That's what we've done. Now, what we'd like to do is investigate more general regions. So the first type of region we're going to look at is called a type 1 region. Let me make this bigger. This is not okay. First one is called a type 1 region. And this is the way we define a type 1 region. But before I show you that, let me just show you what it looks like visually. It's not a rectangle, right? That's not a rectangle. What you'll notice is that this region, which we're calling D, kind of like for domain, that's a D. Notice that for this region, all the points that live in this yellow region, the x values of those points are bounded between A and B, right? So they're all between two fixed numbers. And the G, right, sorry, the y values are bounded between two functions of x, right? So it kind of looks like maybe it's kind of like rectangular this way because it's two constants, but vertically it's two functions that are bounding our points. This is called a type 1 region. When you have a type 1 region, then when you do your double integral over that D is supposed to be to the left. I don't know why it's like that. See if I can fix it. Why that got moved. Okay, so if we're doing double integral over D of our surface with respect to area, remember the area is like that infinitesimal patch on the ground, notice that this right here no longer has constants here, which means you cannot just switch the order of integration like we did last class. We have to follow this order, which means the inner integral must be with respect to y. You do that first, And then your limits of integration are actually going to be functions, not constants. And then once we do that, then we can do the outer integral. It'll be with respect to x and then between those two constants. So that's the new change. I want to do an example. Let's just do this one right here. So find the volume under z equals x plus 2y on the region bounded by y equals 2x squared and y equals 1 plus x squared. Would y'all like to see this first or just get to the... Work it out first? Okay. So find the volume. Do y'all know what this looks like? Z equals x plus 2y? It's a surface, right? What kind of surface? Don't overthink it. It's a plane, isn't it? It's a plane. Because it's x, y, z, all raised to the first power. It's a linear equation. So that's a plane. So we got this plane, right? We want to know the volume underneath this plane, but the region that we're looking at on the ground is the region bounded by these two curves. So let's find D first. Let's find what D is in two-dimensional space, in R2. Let's find the domain on the ground. Let's just see it first. So 2x squared, we all hopefully are comfortable with the idea that that's a parabola, right? Opens up. And then we have the other one, which is also a parabola, right? It opens up, but it's moved up 1. Which one is wider? Which one of these is wider?
1 plus x squared.
That's 1 plus x squared is wider because the number in front here is 1. When we put a 2 in here, what it does is it stretches the thing vertically, which makes it look more narrow. So we have this 1 plus x squared starts here at 1, and it opens like a parabola, but they're going to hit each other, aren't they, somewhere? Like that? They should intersect each other. Here and here. Right, so do you see the region that's bounded by those two? It looks like two little wings or something, right? Like this. That's our domain on the ground. I'm going to try and draw this. Don't worry about drawing. Just pay more attention to what's going on in terms of the idea. I have a plane sitting up here, right? Some plane sitting in space here. And what I'm doing is I'm taking that domain on the ground, I'm just allowing points from this domain to be plugged up in here to this thing. And I get some weird shape up here that might kind of look like a wing. But the important thing is that it creates a solid from the plane down to that region. And I'm trying to find the volume of that solid, right? I'll use the computer to graph this. It'll look better on the computer, but that's what we're trying to do. So I'm going to need to do the double integral over that domain D of f of x, y with respect to area. Now, because this is a type 1 region, why is this type 1? Why is this type 1? I didn't talk about that. Why can I say this is type 1? Look at this region. Can you tell me that the x values are stuck between two constants?
Yeah.
Yes? Do you know what they are right off the top? You could set them equal to each other, couldn't you? Set this equal to this? I think we get 1 and negative 1. Try it. We'll set them equal real quick. 2x squared equals 1 plus x squared. Subtract x squared on both sides. X squared is 1, plus or minus 1. So I know that these are negative 1 and positive 1. So every point in here must live between, the x values must live between negative 1 and 1, but the y values must always be between these two functions, right? These two curves. Between the red and the blue. So I know that my domain, right, is the set of points x, y such that my x is between -1 and 1, but my y is between what two functions? Which one's on the bottom?
The 2x.
2x squared, and the y is less than 1 plus x squared, right? Oops. Do you understand this notation? The domain is the set of all ordered pairs so that your x is between -1 and 1, but your y has to be stuck between those two functions. And then with that, we can set up the integral, the double integral. We're going to come up here, because it's type 1, we're going to say integral from -1 to 1, then integral from lower limit here to upper limit here. So 2x squared to 1 plus x squared. And then what are we integrating? Or f of x, y? What's the actual surface up there? X plus 2y. X plus 2y. And then d what first?
dy.
dy first, then dx on the outside. That's the setup. Can I clarify anything? Yes?
Would we have to put the y equals 2x squared, or is it implied because we have the dy first?
Y equals 2x
You know how
squared.
like we have to like put, oh, x is -1 to x equals 1,
Uh-huh.
and then y equals 2x squared.
Oh, do you have to, okay, you're saying, do I need to state it here? No, it's implied with the
Okay.
dy. Yeah, good question, yeah. These are the restrictions on y. I know that because it's the first integrals with respect to y. These are the restrictions on x because the outer integral is with respect to x. Yeah. Now, when I go and do fundamental theorem of calculus, then when I do that evaluation bar, I will put like y equals or x equals.
Okay.
Yeah. All right, so I think we're there. I think we can actually evaluate this double integral. This should give us the volume. So when I do this double integral, I'm just going to continue up here. When I do this double integral, give myself a little bit more room. Okay, when I do that, I'm going to have integral from -1 to 1. All right. I need to figure out what the antiderivative of this is, right? With respect to y, which means I'm treating what like a constant? X like a constant. Okay, what's the antiderivative of x then? xy. Let's put a bracket. xy. Antiderivative of 2y with respect to y would be? Y squared. Evaluation bar. Y equal 2x squared. Y equal 1 plus x squared. Good. That's our fundamental theorem of calculus. Close the bracket, and then dx, that'll come later. So I'm going to be replacing my y's with those, right? That's going to suck. Okay, -1 to 1. Let's keep this in a bracket. Got to plug in something and then plug in something. And then dx. I hope I'm giving myself enough room here. I'm replacing y with 1 plus x squared. So I have x times 1 plus x squared plus 1 plus x squared squared. So I just replaced that y and that y with 1 plus x squared. And then I plug in 2x squared there, so I get x times 2x squared, and then plus 2x squared, but then that squared. It's going to be messy, right? I mean, it's just polynomials, but it's still kind of messy. Let's go ahead and clean this up. All right, distribute x through here. We get x plus x cubed. Okay, this I'm going to square mentally, right? I'm just going to square that mentally. So that's going to be 1 plus 2x squared plus x to the 4th. And then minus, okay, here I will distribute this negative through, but see, I got to put that together, so that's 2x cubed. And then this will be another minus because the minus comes through here. This will be 2 squared and then x squared squared, so 4x to the 4th. And then all dx. And then I keep going, right? Clean that up. I mean, at this point, right? At this point, it's not that bad. I hope you agree. Minus 3x to the 4th. Minus 3x to the 4th. How many x cubes do we have there? Minus these two and this one, right? So minus 1x cubed, or just minus x cubed? X squared, I only have the plus 2x squared. And then I have plus x. And then dx. Finally, I've gotten it to this. Now, I'm back in Cal 2, doing a polynomial. Yes? Oh, was there a 1? Oh, yeah, I missed the plus 1. Okay, I got the 2x. Yeah. There we go. You know what to do with that? Yes, okay. So we will get to this point where we're just like, okay, yeah, right? Like, yeah, we know what to do. So that's the idea, right? Not too bad. Let's look at the next note. There's the area. There's the region. Oh, let's see it. Do we want to go through that or no? Why don't we just type it into like the computer and get it, right? Like, I'm not going to do it, but right, that we could just type in. Okay, so here's just a visualization of what we just did, right? So we had this region. That was the ground. Oh, where'd it go? There it is. Okay, so there's the ground, right? There was our original domain. There was the ground. Here's the surface, which was that plane, right? Above it or below, could have been anywhere. And then we just plugged these points into this surface, and that creates a solid below it, like that. You take that surface out. Yeah, we'll leave the range there. That right there, that's solid. Now, do you see how it has some little jagged edges on it? That's a limitation of the computer, so don't worry about that. But that right there, we found a way to calculate that volume. So we just did, all right? All right, so now, I'm going to scroll back up. Type 1 region, yes, so this is, if we had two surfaces, surface on top and the surface on bottom, we want to find the volume between them. It's the same idea, you subtract, right? Just like I told you at the beginning of class. But if your region on the ground is a type 1, right? If the region on the ground is type 1, the only thing that changes is, again, you can't change the order of integration. You have to follow that specific this right here. You have to follow that specifically. You have to do your integration with respect to y first, then with respect to x. Okay, we did that one. Let's look at this one. This one's not necessarily any more difficult. It's just to make sure we understand what we're doing here. Z equals x squared plus y squared. Anybody recognize what that is? It's a circle if z was a constant, right? Okay, so it's a circle if z is a constant in two-dimensional space. It's a cylinder if z is a constant in three-dimensional space. But z is not necessarily... So if z is 0, what is it? If z is 0, what is it? Circle of radius 0, which is a point. It's the origin. Yeah. What if z is 1? So you come up 1. Now it's a circle of radius 1. If you come up 2, it's a cylinder that keeps on getting bigger. starting with the point at the bottom. It's a cone. That's a cone equation. Yeah, remember that day we turned the lights out? I said, I hate this day. It's boring because it's all these different things we look at. That's a cone. That's a cone equation. So that looks like a cone, right? So we've got this cone, right? We've got this cone. And we want to find the volume underneath this cone bounded by y equals 2x and y equals x squared. I'm going to start with that domain on the ground. Start with this. Let's try and work quickly through that. Y equals 2x is a line slope 2. Y equals x squared is a parabola that does this, right? So the region bounded by those two is this region right in here. That is a type 1 region. That is a type 1 region. Because when you look at that region, let's call it D, it's the set of points x, y such that, all right, what can you tell me about the x's? The x's are stuck between where and where? 0 and wherever they hit each other, right? Where do they hit each other? Set them equal to each other. Set x squared equal to 2x. You can do it just by inspection. Just guess and answer. 2 works, right? 2 works. Or you can just move things over, factor, and solve. But you get 2, right? You get 0 and 2 are 2 answers. That's where they hit each other. So you can say that the x's are between 0 and 2. And you can say that the y's are stuck between these two functions. The one on the bottom, which is the parabola, x squared, and the one on the top, which is 2x. There you go. That's it. So since that's a type 1 region, we're going to set up the double integral, right? The volume of this thing will be equal to the integrals first from 0 to 2, then from x squared to 2x, and then the integrand is x squared plus y squared, and it's dy then dx. So now that you're seeing double integrals, I mean, they're not as bad as like when you initially think, like, what's a double integral? Ooh, double integral. It's not that big of a deal, right? Yeah, so now we do the antiderivative of the inside, right? Which is, well, let's do it. So we have integral from 0 to 2, bracket. Okay, antiderivative of this with respect to y. So that is a constant, so x squared y would be the antiderivative. Plus, now that has y in it, so 1/3 y cubed is a power rule. Evaluating from y equals x squared to y equals 2x after I'm done with all that dx. Now you're going to plug in here, we're going to simplify, and then we're going to be back in Cal 1, aren't we? Or Cal 1, sorry, Cal 2. All right, plugging in equals integral 0 to 2. All right, I'm going to have two things here. I may have given myself way too much there, but okay, 2x goes in for y, right? So we have x squared times 2x plus 1/3, and then it was 2x, but then cubed. Right, that's what I get when I plug in 2x in for y. And then I have to plug x squared in. So we get x squared times x squared plus 1/3 times x squared, but then cubed. The good news is when I'm done cleaning this all up, it's going to be, you know, this Cal 2 problem, and it'll be a polynomial, and then I can just use power rule and almost there. Integral 0 to 2, bracket. All right, 2x cubed plus 2 over 27x to the third. No, not 2, 8, sorry. 8 over 27. So I cube the 2, cube the x, and then I just divide by, I don't know why I'm not, yeah, 8/3. I'm having one of those days. Minus, now these two together, x to the 4th. And I'll do minus here as well. Yeah, that one, the 1/3 stays, then it's just x squared cubed is x to the 6th. So 1/3 x to the 6th. And then all of that dx. And then we just do each one, right? There's nothing to combine? Ah, shit, there is. But who cares? We can still do it, right?
Yeah.
At this point, equals ... We move on. All right. I don't think there's anything crazy yet, right? Nothing crazy yet. Type 2 regions. There's only 16 type regions. No, I'm kidding. There's only 2 right now, okay? There's only 2. Type 1 and type 2. That's it. So type 2, the difference between type 1 and type 2 is this. Instead of having your x's stuck between 2 constants and your y's stuck between 2 functions of x, now your y's are stuck between 2 constants and your x's are stuck between 2 functions of y.
Gotcha.
That's the only difference between type 1 and type 2. Y'all know what I mean or not? Yes?
I have a question.
Uh-huh.
So, previously, we saw with the functions they met at some points, and those were their
Limits of integration, yeah. Uh-huh.
In this picture, we have 2 functions that are open,
Yes.
but
They, somehow in the problem, I would have to have been given what this is.
oh, okay.
So that would be provided, perhaps, or maybe, I don't know. It would depend. We would have to know. Like, we couldn't just like arbitrarily just choose.
Okay.
Yeah. All right, so going back up to the notation for type 2, the notation here is that, look, you've got the set of all points such that your y is stuck between 2 constants and your x's are stuck between, that's the mathematical symbol for and, or computer science. Y'all use the same thing, I believe. X is less than or equal to 2 functions of y instead of 2 functions of x. So the x is trapped between 2 functions of y, and the y is trapped between 2 constants. That's what it looks like. Well, what changes? We're still trying to find the volume, right? It still means the volume. Now you reverse it, right? Now you have to go with respect to x first, and your limits of integration are going to have functions of y on them, and then you do with respect to y, and those are going to have constants. You are not free. You are not free to switch those. You have to do it in this order. When you're type 1, you have to do it in the order we did before. When it's type 2, you have to do it in this order. Same procedure here. If you're trying to find the volume between 2 surfaces, we just need to subtract those 2 if we're going to do that. Find the double integral over d of xy with respect to area on the region bounded by y equals x minus 1 and y squared equals 2x minus 6. So this is, again, this represents the volume underneath some surface, right? The surface here is the surface xy, whatever that looks like. That's not a plane, right? X times y is not a plane. X plus y would be a plane. This is x times y. It's curved, all right? We want the volume below that, or to the xy plane. We want the volume, but we're only looking above this region. We've got to be able to graph the region, right? We've got to be able to figure out what D looks like. All right, how about y equals x minus 1? That one should be straightforward, right? Just move down 1 and draw a line with the slope of 1. That's y equals x minus 1. That's, I think, the straightforward one. The other one, though, it's y squared equals 2x plus 6. What the heck is that?
It's a sideways.
It's a sideways parabola, exactly. Which way does it open? Because I know, like, with its x squared, If it's positive x squared, parabolas open up. If it's negative, it opens down. With y squared, it's left or right, but which one is it? Positive opens which way?
Positive opens right.
To the right, and then negative opens to the left, right? So if I solve this for x, if I have to solve that for x. So let me first subtract 6, and then let me divide by 2. Do y'all agree that that is what it looks like solved for x? Mm-hmm. So you could say here that this is some function of y. I'll call this h. Doesn't matter which one it is. Yeah, I'll call this h. This one right here. No, I don't want to do it. Let's not call it anything yet. Let's just do that. So if I graph this, I know it's a parabola that opens up to the right like this. And then the -3, what does that do? Shift it. Well, normally -3 for us, back with parabolas this way, -3 would go down 3, right? But when you're sideways, -3 goes this way 3. The only thing I'm just trying to point out here is that I know that this looks like this, okay? Like, I know that that's like the general picture of what I have. And that makes it kind of obvious what the region is, like where it is. Do you see it? It's in here, right? That's your D in there. This looks like a type 2 region because it's not type 1 because this parabola is not a function of x, right? It fails a vertical line test. So these are better off looked at as functions of y. So I do need to see where they hit each other, right? I do need to see where do these intersect one another. So you set them equal. Well, this one is not solved for x yet, right? This one's not solved for x. We need to solve that for x, and that way I can set them equal to each other. So solve this for x. Y plus 1? Okay. So now to find the intersection of these, we get y plus 1 equals 1/2 y squared minus 3, setting those equal to one another. And that's a quadratic equation, isn't it? We should be able to get everything to one side. 0 equals 1/2 y squared minus y minus 4. If it were me solving this, which I am, I'm going to just multiply both sides by 2 first. That's just so I can clear the fraction. I don't like the fractions. Trying to solve that. Does it factor? Minus 4 plus 2? Y minus 4, y plus 2? So what are my two solutions there? 4 and 2. 4 and negative 2, right? 4 and negative 2. So down here at negative 2, that's where they hit. And then up here at 4. Do you see I'm doing this without actually having a true picture? I know enough about this to be able to draw a general sketch.